this is actually a picture I pinched, and this is, trying to draw electric field lines, which is actually a pretty cool 3D visualization where these would be, I don't know, two charged small spheres. Everything tends to be in this unit, and these would be lines depicting electric field. And you might have, we very briefly touched on magnetic field lines in the grade 11 course. And certainly if you put your iron filings over your magnet and you got to see them, well, it's kind of the same thing with electric fields, but we'll talk more about it as we go along. So we talk about fields of force, and I'm trying to draw the parallels constantly between electric and gravitational. Electric field, force field, it's a space, right? They're both a region of space, but an electric force field is where some charged object will feel a force, right? So obviously there's some other charged object nearby creating an electric field. So I drop some little sphere in there, and it's going to wish it was moving towards or away from the originally charged object. And it's not that different than, around an object with mass, right? So the sun is sitting in the middle of our solar system, and someone plops down a new planet. Well, that planet is going to be attracted to the sun, right? Because the sun creates a huge gravitational force field, or the Earth does as well, or any object with mass does. And so that's all a field is, right? And we live in a gravitational field. We live in a magnetic field. We live around electric force fields. Of course, Earth creates a gigantic magnetic force field that we're living in as well. We don't feel that very much, but we certainly do feel the gravitational force field that we live in. So field lines are lines that are drawn, and we don't worry a little bit. Like, there's always a multiple choice question related to this, but they're lines that are drawn around an object, and they're supposed to visualize where, okay, so say I have some charged object sitting right here, right? Well, this line tells me that if right where my mouse is, if I dropped a positively charged object right there, where would it go? Now, there's no arrows on this, so it's not that useful. Usually there's arrows on them, but it would tell me that at least it would follow this path, right? And so we always specifically draw them to visualize where a positive charge would go. Okay, some rules related to them. We never draw them to cross. They never cross each other. If they're more dense, you see how they're closer together here? That's because the electric field will be a lot stronger very close to this object, right? Over here, they're not as dense, meaning they're not as close together, because they're far away, right? That's the same as gravity. Gravity would be less here than it would be right there. That's all it's saying. Okay, and this idea that you draw arrows on them just to indicate where would a positive charge go, and that's just a convention that some physicists made up along the way, that we're going to say that the arrows represent where a positive would go. So just how we would draw them. Say you have a positive object, charged object. Well, you would draw sort of radiating out like the sunshine, I guess. You would draw arrows away, because if I stuck a positive charged object anywhere around here, it would move straight away from there. Unlike a negatively charged object, it's the same idea, but the arrows point towards it. And it's just really important with electric field that you keep that in mind. We always define electric fields as what a positive charge would do. So you can have field lines with more than one charged object. So say you had two positive charged objects here and here. This is a picture of what the field lines would look like. Because if you stuck something right here, well, it wouldn't know what to do. It would get stuck, right? Maybe it'd take off right or left, most likely, I guess, just to get away. But if I stuck a positive charge here, like, it doesn't follow the same pattern. There's an interaction of the fields. Okay. If you have, this one has a special name. If you have a negative charge and a positive charge sort of placed near each other and drew out the field lines, they give that a special word called a dipole. So a dipole, I've used that on a test before, which one of the following looks like a dipole or something like that. And so, and the difference, of course, is, if I stuck a positive charge right here, it would move straight to the negative. But if I stuck a positive charge here, could get stuck, but it might try to move radially one way or the other. Okay, so field strength. In gravity, let's look over at the gravity first. Gravitational field strength It's a vector, and it points to, you know, it points, like if you're near Earth, it points towards the center of the Earth, because an object with mass will want to fall towards the center of the Earth, right? We give it the symbol G, and it has units, Newton per kilogram. Okay? Electric field strength is a vector as well, and it always points in the direction, like I said about the field lines, where a positive charge would go. Somebody chose positive, you know, just because they did. There's no reason why positive and not negative, but I had to choose one. It has a symbol, it's called epsilon, but it's not an E, so to speak. It's a cursive, looks like a cursive capital E, and it's a vector as well. And its unit, and again, you should look at the parallel. Gravitational field strength is newtons per kilogram, where kilogram is like mass, right? Well, electric field strength is newtons per coulomb, right? Because coulomb is charge. So and it tells me then, you know, it's force per unit, positive specifically charge, and the positive is reflected in the sign, in the direction. And gravitational field strength is a gravitational force per unit mass. Okay, so it's how much force 1 coulomb of charge, positive 1 coulomb of charge would feel. This is how much force 1 kilogram of mass would feel. So the formula, again, looking at it is the same. If we look over here at G, we know that G, you know, follow me down, you've done this before, but gravitational field strength is, you know, the constant times the mass of the object creating the field, like, and we always said like the mass of the planet or whatever, divided by, you know, the radius of the planet squared, right? Electric field, exact same. The proportionality constant times the charge of the object creating the field, divided by the distance to the center to center difference, distance squared. And by that I mean, like, if, you know, from where you're measuring the field strength to the center of the charging object. Just like it's where you're measuring the gravitational field strength to the center of the Earth or whatever. And the direction is, again, where a positive charge would go. So you have to decide that. It's not part of the equation. You look at the situation, you decide which way a positive charge would go. So let's look at an example. So we have a negative charge, and it's placed down somewhere, and it's feeling an electric force of 3.2 newtons acting to the left. And we want to find the magnitude and direction of the electric field then. So that's pretty easy. It's just the electric force divided by the charge, right? So if this many coulombs is experiencing that much force, how much force would 1 coulomb feel, right? And so it's a big number, and they tend to be, by the way, they tend to be in the order of times 10 to the 5 or 10 to the 6, okay? And then when it says direction, it's the direction a positive charge would feel. So if a negative charge is feeling a force to the left, that means that my field answer has to be to the right, okay? So let's review that again with the direction. It says here that a negative charge feels a force to the left. That means that the field strength, by convention, you can calculate it. Then you have to say, well, if the negative charge feels a force left, then a positive charge would feel a force to the right, and that makes my field right, only because you choose what a positive charge would feel. Oh, I'm going to check mark that, though it's hard to know. What I can say is that they're typically in this order, times 10 to the 5 or 10 to the 6. But okay, let's do one more example in this note. So now we're saying we have a location. There's no charge sitting here. It's just a location in space, kind of like choosing the top of Mount Everest or something around Earth. It's just a spot, okay? At a certain point, and there's an electric field it's sitting in. The magnitude of the field is 12 newtons per coulomb. Calculate the magnitude of the force. So say I stuck a very tiny charge, 0.25 microcoulombs, right here at that location where the field strength is this. Okay? Well, this is actually a very similar question to me saying, find, given that on the top of Mount Everest, the gravitational field strength is 9.79. Find the force of gravity that would be experienced by a 10 kilogram dog at that location. And you'd multiply 10 times the field strength. That's all you do. Okay? It's the same thing. You take the field strength, you multiply it by the charge. Oh, look at that. I made a boo-boo. Well, let's pretend that that's 6 because I'm not redoing it. So, pretend that's 10 to the negative 6. Okay? Stupid me. And you get your force. Okay? 6. Okay. I guess I can't check mark it because I screwed up. Okay, anyways, that's the last of that. That's the first 2 applications. I have more examples, but we'll just stop this video at that point.